chapter summary for chapter 18 using OpenStax. I'm going to start off with a demo. I have here a little stick. I have here a piece of Mylar. Let's see what happens. Just watch what happens. Magic stuff happens. So this is a tiny little electrostatic generator, and this is a piece of Mylar that I can charge. And if they have the same charge, they repel. And this is an example of electrostatic. So we've got a bunch of stuff to do here. I'm not going to solve any problems. I'm just doing a chapter summary. Problems will be in a different video. Okay, so let's start off with the fundamental idea of charges. Because if you look around you, and there's a lot of stuff in here that's more conceptual, and I'm going to focus more on the mathematical stuff, but I want to talk about some of the conceptual stuff too. If I look at this chalkboard, the chalk, my face, which I can't see, the camera, which I can see, there are three things, and all of those are made up of just three things. A neutron, a proton, and an electron. And it's kind of amazing to think about that, right? There are other things. There are other fundamental particles. Neutrons and protons are not technically fundamental. We can break those up into other things. But everything that you see around you is made up of those three things, and by combining them in different combinations, we make things like carbon and oxygen, water, bananas, chalk. Do I have chalk on my head? Okay. So the other important thing to realize is that these fundamental particles are charged. The neutron has no charge, but the proton and electron have equal and opposite charges, and we use this. E is 1.6 times 10 to the negative 19th coulombs, and I'll spell it out, Coulomb. So this is our fundamental unit of charge. The electron has a charge of negative E. This has a charge of plus E. They're equal and opposite charges. Now, I do want to say one other thing because the book has it in there too. It says, oh look, there's a proton, there's a neutron, there's another proton, there's another neutron, and then there's electrons that are orbiting around there. This would be helium, right? And that's a fine model. I want to point out it's not real. Okay, we do not have atoms as tiny little solar systems, although that was one of the original ideas. It's way more complicated than that. Okay, but there is an electric interaction between these charges, just like there's an electric interaction between the Mylar and the little charge generator. Okay, so those are our fundamental charges. I do want to point out that there is a positive charged electron. There is a negatively charged neutron. These we call antimatter. So the negatively charged proton is called an antimatter proton. The positively charged electron is called antimatter electron, or a positron because it sounds cool. So that's a positron. But it does exist. Now I do want to point out one other thing, because you can't create or destroy charge. If I take a neutron all by itself, this is a great example. Suppose I have a neutron all by itself. It's right here. It turns out that that's not stable, and it will decay into two things. Actually three. It will decay into a positive proton and a negative electron. So the charge before this was 0, the charge afterwards 0. There's actually another particle produced, a neutrino, but that's not important right now. So you cannot just create a proton by itself, but if I create a proton and an electron together, then the net charge is constant and the net charge is conserved. The same thing's true if I have an electron and a positron. They're equal and opposite charges. They can annihilate and create energy. And that's fine. They're gone. They're gone. But I didn't destroy any charge. What's next? Let's talk about conductors and insulators. So we have two types of materials. I have a material like this as a conductor, and And then conductor, we have positive cores, the nucleus of the material, and they all have an electron, and these electrons can actually move around, and that's what makes it a conductor. So conductors are things like aluminum, iron, copper, gold, silver. Metals are conductors. Some other things like graphite can be a conductor, but in those cases we have free charges that can move. Now in an insulator we also have charges, but in this case those are bound together, and they can do interesting things like separate a little bit, but the charges can't move around. So insulators would be things like glass, plastic, wood, styrofoam, rubber. Okay. Now, if I want to charge two objects, if I want to get something charged, I can do that. Rubbing things together, two different types of material together, can cause them to be charged. That's what's happening in here. If you hear this, there's a motor in there that's rubbing things together and it's building up a charge. And where does that charge come from? It actually comes from me, because the button right here is conducting, so I can get charged to this. But if I want to have something that's negatively charged, it has just extra negative charges on there. If I want to make something that's positively charged, then I don't add extra positives, because those would be in the nucleus. I can't really move those around. So it would just be fewer electrons. I take some of them away. Now that one's positively charged. Okay. Now, so I can charge things by rubbing or by contact. And that's how you get things to be excessively charged. Okay, there's a lot of interesting stuff about matter in there, but I want to get into the more important things. And that is the force between two charges. And this is what we call Coulomb's law. Suppose I have a positive charge Q1, and I have another positive charge over here, Q2, and they're separated by a distance r. The two charges will repel each other. So I could say this is F2 on 1, it technically is a vector, and this is F1 on 2, it's technically a vector. I can calculate the magnitude of that vector, that force. Either one of them, they're the same, right? When I have two objects interacting, the force that A pushes on B is equal to the force that B pushes on A. That's Newton's third law. Forces come in pairs. I can calculate the magnitude of this. F is K Q1 Q2 absolute value over R squared, where K is the Coulomb constant, 8.99 times 10 to the negative 9th newtons meter squared per Coulomb squared. And Coulomb is a unit of charge. I said that earlier, right? So this is what we call Coulomb's law. It says that as those charges get further away, the force gets smaller. As you get them closer together, the force gets greater. And as you change the magnitude of their charges, the force also changes. And this is a very important constant. And actually we can write this as 1 over 4 pi epsilon naught. And it turns out that epsilon naught shows up in other places, so it's useful. But we'll always call it K. That's what the book does, so I'll do it that way too. Now, yes, that does look like the gravitational force between two objects, if you remember that from the last semester, where that was G mass 1 mass 2 over R squared. What's different is that the gravitational force between two masses is always attractive. This could be attractive or repulsive. If I change one of these to a negative charge, then this would change directions. Both of these would change directions, and it would be an attractive force. This equation isn't the best way to write Coulomb's law because it's not a vector equation. But in this curriculum, writing it as a vector equation becomes a little bit more complicated, and we'll deal with the things in the easiest way that we could. Now, what if I have more than two charges? Well, forces obey the superposition principle. So let's say that there are three charges. So I have right here, I'm just going to make up something, Q1, here's another one, Q2, and then I'll put a negative charge on here, Q3. And suppose I know all those distances, and I want to find the force on Q1, Q2. So these two are going to repel, so I'll write this as F1, 2, and these two are going to attract, and I'll write this as F3, 2. So I have two forces from the two interactions. These two interact, and those two interact. And then the net force is just the vector sum of those, and it'd be like this, F net. Okay, so but you have to treat those as vectors, so you would have to know the direction and the magnitude, and it's not always a trivial problem, but that's what we have. Now, the next thing I want to talk about is the electric field. This is, there's two really big ideas in this semester. The electric field and the magnetic field and how they relate. They're huge, okay? I want to take a step back and talk about the gravitational field. I should spell that with a capital G. I don't know why I did the capital R. G, gravitational field. So suppose I have the Earth and I have a ball right there of mass m. I can calculate the downward force F, I'll call it Fg, as mg. So G is the gravitational field that has a magnitude of 9.8 newtons per kilogram. It's the force per unit mass. Since the force depends on the mass and this other constant, that constant is the force per unit mass. If I double the mass, I double the force. And that's the gravitational field. It is technically a vector. You didn't always write it as a vector, but it's a vector. Okay? It's the force per unit mass. How can I find the gravitational field? Well, if I take some mass and I put it there, and I measure the force and I divide by its mass, I get it. So G, the magnitude, would be the force divided by the mass. And that's the gravitational field. Now, what if you move further away from the Earth? Well, in that case, I have to use a different expression for the gravitational force. Here's the Earth. Here's my test mass. Here's the vector R. And then I had F, the force on that mass, is G m times the mass of the Earth over r squared. If I divide that, I can say G is F over m, and that's G, mass of the Earth, over r squared. So it's still the gravitational field. G is the gravitational field. It's the force per unit mass. Electric field. So we have the same thing with the electric field. So remember that if I have two charges, Q1, Q2, F, it's the magnitude. I'm just gonna write it as this. Q1, Q2 over r squared. What if I take E as F over Q, let's say Q2, right? I want to find the electric field due to this one, so I'm going to divide by that, and I get the electric, that is the electric field. It is the force per unit mass. Now, that's a vector, and that's a vector. So electric field is a vector. Again, it's a limitation of the course that they want to write these forces as scalar values, but it is a vector. And so is electric field. So electric field is the force per unit charge, and it would have units of newtons force per charge, Coulomb. That's the electric field. And since I know the expression for the force due to one charge and I divide by that charge, I get the magnitude of the electric field due to a single point charge is K Q over r squared. It is a vector, but that's just the magnitude. The electric field. So let's just think about what this would look like. The electric field, we can visualize the electric field around some object. So imagine that I have a positive charge, and I'm over here, I want to calculate the electric field. Well, I'll put a positive charge there, and it'll experience a force this way. I divide by the value of that force, and I get the electric fields that way. So over here it's this way, there it's that way. And so this is what I'm drawing is what's called the electric field. It's a field. So this is E. So it points away from positive charges. If I have a negative charge, well, if I take that same charge and put it right there, it's going to experience force pulling it towards there. So a negative charge would have an electric field pointing towards it. And as it gets further away, the value of that charge decreases. What if I have more than one charge? Well, again, the electric field obeys the superposition principle. So suppose I have two charges near each other. I can find the total electric field due to those two charges. Suppose I have a plus right there and a minus right there, and I want to find the electric field down here. Well, this is going to make an electric field going that way. This is going to make an electric field going that way. And when I add those two together, let's call this E plus, E minus, and this would be the total electric field E. So you still have to add them up. Now, how do you add vectors? That's something that we need to remember. And I'm going to give you a quick vector review in just a second. Superposition. Let me give you, let me say this, just because I put it in my notes and it is in there, and it is fun. There's this thing called, if you apply a large enough electric field in the air, then that air turns from an insulator into a conductor. And when that happens, you get a spark. So you've seen sparks before, right? That happens when the electric field exceeds 3 times 10 to the 6 newtons per coulomb. And we call that the breakdown electric field of air. And it's just a useful problem that we can use in different situations. Okay, let's review adding vectors. And I do not think the book does a great job here. But I'm biased, and I like to do things my own way. But I try to do it along with the book. So let's just say vector versus a scalar. So you hopefully have looked at these in your previous physics course, but if you didn't, this is a quick review. So a scalar is a thing that only has one thing to go with it. So scalars are things like time, mass, charge, energy. They're just one thing. A vector has multiple dimensions. So it doesn't just matter what it is, but what direction it's going. So you've seen this before with velocity, position, acceleration, force, and electric field. So, but how do you represent a vector? Let's just draw a vector, okay? Let's use a position vector because it's easier. So here's the xy axis. Suppose I have some point right here. I can represent that as the vector r. And it has some distance from here to there, and it has some angle with respect to the x-axis theta. I'm reviewing here, not the full details, okay? We can represent this vector as a sum of a vector in the x direction plus a vector in the y direction. Why do we want to do that? Well, if you break a vector into these x and y components, it's easier to add them. So we'll call this r x hat, r y y hat. And so this is just, the x hat just means in the x direction, and that's a scalar value. Y is a scalar value, and that's in the y direction. So I can write r as r x hat plus r y hat. How can I find a relationship between the magnitude of the vector r, rx, and ry? I can use trig. So remember that we have these cosine sine functions. So if I take the sine of the angle theta. Sine is defined as opposite over hypotenuse. Well, the opposite side has a length ry. The hypotenuse has a magnitude r. So I can solve this and I get ry is r sine theta. I can do the same thing with cosine. Cosine theta is the adjacent over the hypotenuse. So that's rx over r. So rx is r cosine theta. So this means that if I have a vector and I know the angle with respect to the x or y axis, I can find these x and y components. Now be careful. Two things. What if I had this? Well, in that case, this is my right triangle. So in this case, the opposite side is the x component, the adjacent side is the y. So don't think this is always ry. You have to look at the picture. Next, what if I have a vector over here? And this is the angle. Well, again, I have the x's sine, but it's negative, right? Because it's going in the negative x direction. And the y component will be positive. So you need to look at your picture and look at your angles and determine if your components are positive or negative. Well, why do we even care? Suppose I have two electric field vectors. E1 is E1 x hat plus E2 y hat. E2 is E2 x hat plus E2 y hat. If I want to add those two vectors together, E1 plus E2, I can add their components because the x's are in the same direction. So that I can just add them. The y's are in the same direction. I can just add them. Now they might be negative and that's fine, but I can do that. So this would be E1x plus E2 x hat plus E2 y plus E2 y hat. Now what if I want to find the magnitude of this total vector? I'll call it just E. The magnitude of E, now that I know the components, I can go back the other way. I know the adjacent side, I know the opposite side, I can find the hypotenuse using the Pythagorean theorem. So this would be E1x, I'll just call it EX, right? That's the total. EX squared plus EY squared, and that's that. If you need to find the angle, you can say the tangent of the angle theta is opposite, which is most likely EY over EX. Okay, that's that. I'm going to post some problems. We're going to do some problems. It doesn't really make sense until we do problems. Oh, I did want to show you, there is a really great PhET simulator, but I'll maybe play with that later. If you read through the book, there's some simulators embedded. Play with those. They're really great. I think they're awesome. Let's see. Can I pull this up real quick? Let's see. Yeah. Okay, let's do physics. Okay, let's switch to the computer. So this is PhET, and I'm going to just turn off these. Don't want motion, sound, work, energy, light. I want that one. Okay, and let's go down here. Charges and fields. You can't see it. Let me make this a little bit smaller. I should have fixed this all beforehand, but I didn't. Okay, so here we can just move some charges onto our playing field. There's a positive charge, and it shows the electric field at all these different locations as a vector. And then I can put it in a negative charge right here, and you'll see that I get this completely different shape of patterns because for each one of these locations, this vector points in the vector sum of the positive and the negative. What's that do? Values? No. Don't worry about that. I can put another charge here. So you can build up a whole bunch of things and play with it. I thought that was going to be more interesting than it was, but you should play with that anyway. Okay, so that's that for chapter 18. I'll post some homework problems and some practice problems, and we'll do that. But other than that, that's that. And I don't have to stop. There it is. Stop button right there.